So we've now seen that the Earth is in balance in relation to its energy fluxes. Incoming equals outgoing. But you know that while that might be true for the whole Earth, it's not true for individual places on the Earth's surface, or at different times of the year, or even different times of the day. You know that temperatures change depending on where you are and what time of year or day it is. So let's have a look at some of the reasons why that happens, and that will help us to explain some of the basic features and processes of weather and climate. Okay, so the main reason, or I guess the most obvious reason, is differences in atmospheric composition, clouds. When it's cloudy during the day, it's usually colder. When it's cloudy at night, however, it's sometimes warmer compared to a clear night. And that's because, as that energy is escaping from the Earth's surface, that it's being trapped by some of those clouds overnight. You probably noticed that. You get frosts on clear nights during winter. All right, so that's one reason why you get differences on the Earth. The other is what's known as surface albedo, and that's just a fancy word for how much energy is reflected. And it differs depending on various factors. So the albedo is just the proportion of solar radiation reflected from a surface. Okay, so it's just the relationship between what comes in and what goes out. The more that goes out, we say that's got a higher albedo. And this table here just shows some of the typical albedos of different landscapes. So it's lower for things like dark and wet soils, so they absorb more energy and reflect less. But for snow and ice, they have higher albedos, and fresh snow, because it's so white, reflects almost all of that energy back. Water's an interesting one. It changes depending on the angle of the sun. Now, you probably know this if you're standing near the ocean on a late afternoon in the, in the west, or early morning in the east of the continent, or looking in those directions. You can see that light that the sun reflects off the surface of the water into your eye. But when the sun is high in the sky, that energy actually goes into that water. And that has an important role in some differences, which we'll see a bit later on. Okay, so that means, so one good example there, as we will see later on, is that the snow and ice on the Earth's ice caps helps to keep that part of the world cold, because the energy is actually being reflected off the snow and ice that exists there. Okay, so the time of day and time of year can also have obvious effects on the energy fluxes. So let's have a look at time of day. So you know that during the day it's warmer, and during the night it's colder. Well, why? Because the sun's energy is coming in during the day and going out at night. So we can say that during the daytime the energy flux is positive, and during the night time the energy flux is negative. But in balance it's, on a whole, zero. Now let's just have a look at that in a bit more detail. So this graph here just shows you the incoming solar radiation. And at midday, when the sun is highest in the sky, that's the maximum incoming solar radiation on any particular day. But when we have a look at temperature, it's not at midday. The highest temperature is not at midday every day. There's usually a lag of an hour or so before you get the highest temperatures, and you've probably experienced that. Now, why is that? Why doesn't it match the time when the solar radiation is at its maximum? Well, the reason is, and you have to remember, that the atmosphere is not heated by that incoming solar radiation. Remember that it's shortwave radiation which passes, on the whole, through the atmosphere and doesn't heat up any of the gases in the atmosphere. But what does heat up the gases? It's the Earth's surface that heats the air closest to the Earth's surface. Now, there's a lag between the time that the Earth is hit by those solar radiations and the time it starts to re-emit energy. And you can see this figure here, the blue line, showing you when the maximum of the outgoing terrestrial radiation is, and that's at sort of 3 o'clock in the afternoon. So there's a time lag that takes the Earth time to warm up before it then starts to re-radiate its maximum radiation, and therefore at that time it'll be maximizing the heating of the atmosphere. Okay, so that's the temporal differences during the day. The other, and we'll have a look at differences during the year when we have a look at seasons in the next topic. Now, the other reason that you get differences is the composition of the Earth itself. What do we mean by that? Well, putting it simply, something that you've experienced. Why is water cold on a hot day? So you go to the beach and you run across the sand because it's kind of hot, and you jump into the water because it's cold. Okay, so we've all done that. Why? Why is the beach, why is the sand hot and the water cold? It's due to its different makeup, the atoms that make up that material. Okay, let's have a look at this in a bit more detail. Try and stay with me because it does get a little bit complex, but it's really useful to understand these basic principles because it helps us to understand what's happening in the climate and having a look at the basic weather processes. Okay, so the first concept we need to understand is heat capacity. Now, I'll just read this out. Heat capacity. The specific heat capacity of a material is the heat energy needed to raise the temperature of 1 kilogram of the material by 1 degree Kelvin. Now, the relationship between Celsius and Kelvin, they're just different scales. You can look it up if you want to know what Kelvin is, but the main thing to understand is that 1 degree Celsius is equivalent to 1 degree Kelvin. So it's the same amount. The start and finish points are different. All right, now if we look at heat capacity, the units of heat capacity, as in how much energy is required, is joules per kilogram. So the energy is joules per kilogram per Kelvin. Okay, so it's the amount of heat energy needed to change the temperature of a body. And it depends upon the material of the body, water, sand, earth, ice, whatever, the mass of the body, how much you've got of it, and the initial temperature of the body. So we're going to remove two of those variables and have a look at the heat capacity, specific heat capacity of some different materials. So we're going to remove the mass and just look at 1 kilogram, and we're going to start at the same temperature. So specific heat capacities for different materials at 300 degrees Kelvin, which is about 27 degrees Celsius, raising it by 1 degree, raising 1 kilogram by 1 degree Kelvin. Air requires 1,158 joules per kilogram, or 1.158 kilojoules. Okay. Soil varies depending on whether it's wet or dry. Sand only requires a very low amount of, or relatively lower amount of energy to raise it by 1 degree, only 835 joules per kilogram. But if you have a look at water, it requires 3,985 joules per kilogram to raise it by 1 degree. So it requires a lot more energy. Sand doesn't require very much energy to raise the temperature. So that's why when you're going to the beach, the sand is really hot and you run across it to dive into the water, which is much cooler. That beach is receiving the same amount of energy, no matter where you are, whether you're standing on the sand or whether you're in the water. But sand is heating up much more quickly because its specific heat capacity is lower than water. All right. So we say that water has an unusually, compared to other materials, high specific heat capacity. Okay, now we're going to have a look at different types of heat. Did you know that there are different types of heat? Yes, there are. The first one you have experienced, and it's called sensible heat. So sensible heat is just the amount of heat that is stored in a material due to its increase in temperature. And you've felt that. You want to boil some water, you put the kettle on the stove, the water starts off at 15 degrees, and you turn on the gas, you're adding energy to it, you're transferring heat energy from the gas to the water, and you're increasing its temperature. And you can feel that the heat, that's the sensible heat that you can feel. But there's another type of heat that you can't feel, and that's called latent heat. It's hidden heat. Now this can get a bit technical, so try and bear with me. We define latent heat as the heat energy stored in a substance, or heat energy that flows to, or in fact from, a substance without a change in its temperature. So what does the heat energy do? Well, it changes the phase of the substance. Now, phase is just a fancy word for whether something is a solid, a liquid, or a gas. So we'll stick with water, whether it's ice, whether it's water, or whether it's water vapor. So it's the energy that's used to transform from one of those phases to another. Or it's the energy that is released as you go back the other way. Let's have a look at a graph and see if that helps. So here we have liquid water at, let's say, 15 degrees Celsius. You put it on the stove, you light the stove, you're transferring heat from the gas into the water, you're raising its temperature, and that's the sensible heat that you can feel, this part of the graph. Then it gets to 100 degrees Celsius, and what happens? It starts to boil. If you had a thermometer in that water, even though you're adding more heat to the water, it's not changing its temperature. That water will stay at 100 degrees. It'll start to boil off, evaporate off, until eventually all of the water has evaporated off, and then the temperature of that gas, if you had trapped the gas and were able to still add heat energy to it, would then increase. So that heat energy then is stored in that water vapor. You can't feel it, okay? It's actually stored. So if you turned off the gas and it stayed as water vapor, that heat energy is in that water vapor. It's being stored in it, keeping it a gas. Those molecules are moving around really quickly as a result of the heat energy that you've put into that water vapor, and it's now a gas. If you were then to go in the opposite direction, from water vapor to liquid, condensation we call that, then that heat energy is actually released. It's released from those molecules of H2O, and you can then feel that energy, because that's the energy that is being released. And the same thing happens when you go from liquid to a solid. So hopefully you've got at least some of that. So just need to understand that latent heat is the heat energy that's stored in the substance that you can't feel until it changes its state again. All right, stop there.